You. So it's 11. Let's start. Today we have pleasure of having Ping Sun presenting a joint paper with Elena Parellina, stable networks and dynamic network formation with group partitioning. Let me remind you that the session is recorded. So if you want to put off your camera, feel free. Thank you, Ping, for accepting our invitation, and the floor is yours.
Okay, thank you so much, Professor. And also, please allow me to say it's my really great honor to present in this series of seminars. So hello, everybody. The main topic of my presentation today is network games with group partitioning. I'll give this report from the following sections. First, I'd like to introduce some literature on this topic, and next introduce some basic notations, and then describe two models of network games. One is from the static version, and the other is from the dynamic version. And finally, I'll conclude and show our future research issues. There are several papers on the topic of network games, where the player's set is partitioned into groups. For instance, in this Gallo's work, there are several groups, and in each group, there are cognizant players and ignorant players. Cognizant players know the exact network structure of players, and ignorant players just know the existence of some links that are associated with those players that are in the same group with them, which indeed influence the utilities of players. And the author mainly consider the condition for some networks to be pairwise Nash network. And in this second work, there are only two communities, or we say two groups. And the cost function is defined in the way that the cost between players in the same group is much lower than that between the players in the different groups. And the author mainly consider the conditions for some special network structures to be pairwise stable. And in this work, there are several teams, or we say groups, and each player needs to pay the cost for any connected player. So the cost is related with the distance between the two players. And the concept of team pairwise stability is proposed in the sense of which the link is formed or severed on considering the interests of the benefits of the whole team. Well, now I'd like to talk about some notations. First, about network. Here N is the finite set of players. G, a set of some links, is a network structure. And Nij is the set of neighbors of player I in network G. And a sequence of players I1 to Ik is a path between the two players. If for any two near players, there is a link between them. And we see two players are connected in this network if there exists at least one path between them. And the DIGG is the distance between the two players. Actually, it is the number of links in the shortest path. And we use this symbol to denote that players I and G are connected in network G. And C, a subset of network G, is called a component. If for any two players who have links in this set, they are connected through the links in this set. And for any link IG in network G, if it involves at least one player who have links in this set, then this link must exist in this set. And actually, a component of network G is a maximally connected subnetwork of network G. And CIG is the component containing all the direct links of player I. And we see a network G is connected if for any two players, they are connected in this network. And we see a network is minimal if the deletion of any link would disconnect at least one pair of players who are connected before. And then about group partition. Here, delta is called a partition of set N if the union of all these sets is N, and there is no intersection between any two sets. And pi I is the label of the group that player I belongs to. In other words, if player I belongs to group NK, so K is pi I, is the label. Well, here I'd like to remark in advance that the label is very important. It somehow represents the social position or location of the players in this group. And also the difference between the labels of two groups is very important too, because it represents the social distance between the two groups. And NIKG is the set of neighbors of player I in this group. And a network is an inner star network regarding a given partition if players in each group form a star network and the players in different groups are not connected. And a network G is partially minimally connected regarding a given partition if players in the same group form a minimally connected network and the players in different groups are not connected. Well, to better figure out the shapes of the three kinds of networks, let's see these figures. Well, given a partition of three groups, the first network is an inner star network regarding this partition because players in the same group form a star network and the players in different groups are not connected. And I forgot to say that the players in the same color are in the same group. And the second network is an inner complete network regarding the partition. Because the players in the same group form a complete network, and the players in different groups are not connected. And the last one is a partially minimally connected network regarding this partition, because the players in each group form a connected and minimal network, and the players in different groups are not connected. Well, now let's come to model 1. Well, because in model 1, we define the utility of each player as the difference between benefit and cost. So we introduce two cost functions first. Under the first cost function, the cost for link ij of player I depends on the label difference between the two groups. So F0 is the cost between players in the same group, and F1 is the cost between players in the nearby groups, and so on. Because function f is positive and non-decreasing, so we can see that the larger the difference, the larger the cost. Well, let's imagine a background. Well, suppose that people at the similar ages are in the same group. For instance, teenagers are in group N1 and adults are in group N2, and the retired people or old people are in group 3. And generally, we can think that it is more difficult for teenagers to communicate with their grandparents. And it is easier for teenagers to talk with other teenagers. So this is a short background. And under the second cost function, if the two players are in the same group, then the cost is F0. And if the two players are not in the same group, and the cost is the difference between two items. And the first item is just a copy from the first type. And now let's pay attention to the second item. Neighbors of player I in network G. So we can see that among all the neighbors of player I, if the proportion of players who are in the same group with player G, the proportion is larger, then this part is larger and this cost is smaller. So we can see that under the second cost function, players may prefer to form more links with players in a certain group to decrease the average cost with them. And with the two kinds of cost functions and the two kinds of benefits, we define 4 utility functions. In case 1, the benefit is with decay. It means that player I gets unit 1 from each of his neighbors. And for any other connected player, the benefit unit 1 decays through the path, and delta is the decay factor. And the first cost function is adopted. And in case 2, the benefit is without decay, which means that player I gets unit 1 from any of his connected player. So there is no difference between neighbors and any other connected player. And the first cost function is adopted. And for case 3 and case 4, the second cost function is adopted. So below, we'd like to study stable network, and we adopt the definition by Jackson and Wielicki. So given partition delta and the utility function, a network G is called stable if and only if 2 conditions are satisfied. On the one hand, for any link IG in this network, both players I and J cannot strictly gains by deleting the link. And on the other hand, for any link IG which is not in this network, if player I strictly gains by forming the link, then definitely player G will strictly lose by forming the link. So the link IG cannot be formed by the consent of the 2 players. Well, below, we'd like to compare the influence of the 2 utility functions on stable network. First, case 2 and case 4. Both benefits without decay, and case 2 is the first very ordinary cost function, and case 4, the very special cost function. Well, we aim to compare the 2 cost function, so the situation for benefit is the same without decay. Let's see the results. Well, proposition 1 says that in case 2, any non-empty stable network is stable. And under case 4, if F1 is bigger than 1, the cost between players in the nearby groups is bigger than 1, then any non-empty stable network is minimal. Well, the difference is obvious. There is no constraint for this result, but there is this constraint for this result. And in case 2, if the cost between players in the same group is bigger than 1, then empty network is the unique stable network. And in case 4, only these conditions are satisfied, then we can assure that empty network is the unique stable network. Well, to feel the difference brought by the 2 results, let's see 2 numerical examples. Here in case 1, the cost between players in the same group is 1/2, and the cost between players in the nearby groups is 1, which means that the condition here is not satisfied. So it is possible for us to find a stable network that is not minimal. So let's see the network G in figure 2. There are 5 groups, and players 1 and 2 in group 1, players 3 and 4 in group 2, and so on. After our check, we find that this not minimal network is stable. But if we change the cost F1, make it bigger than 1, then we check that this network is not stable anymore. It becomes unstable. Well, then let's see example 2. Here the parameters are given so that the condition in proposition 2 here is not satisfied. So it's possible for us to find a stable network, not empty. So let's see the network G in figure 3. There are 7 players and 2 groups. There is only 1 player in group 1, and all other players are in group 2. And we check, we find that this not empty network G is stable. Well, why is it? Why cause this not empty network is stable? Because player 1 forms 6 links with players in group 2, and so that the cost is decreasing. Well, originally the cost should be 3 over 2, 1.5 bigger than 1. Now, the cost that player 1 needs to pay for such link is just 3 over 2 minus 5 over 6. It is much smaller than 1. This is the cost for this network to be stable. Well, now let's continue to compare. Here, M dash at the bottom is the minimum number of players among all the groups. And M dash is the maximum number of players among all the groups. And propositions 3 and 4 separately give the different sufficient conditions for any stable network to be minimally connected. We can see that this condition is much strict. And if the number of players is very large, then only if F0, the cost between players in the same group, is very low, then we can sure that any stable network is minimally connected. And the theorem 1 says that regardless of the utility function, when these conditions are satisfied, a network G is stable if and only if it is partially minimally connected regarding the given partition. Well, to feel this difference, let's again see a numerical example. Here, the parameters are given such that the conditions here is not satisfied. So it's possible for us to find a stable network not minimally connected. So let's see this network in the figure. There are two groups. Players 3, 6, and 9 are in group 1, and all other players are in group 2. And we find that this network is stable under case 4. Well, there is a very interesting point in this example. We can observe that players 3 and 6 prefer to form links with player 2 and 4 who are in the different group with them with a higher unit cost rather than form a link with player 9 who is in the same group with him with a lower unit cost. Why is it? Well, because forming this link will increase the average unit cost for the two links. Well, for these phenomena, let's think about a background. For example, there are some people are learning a fresh or new foreign language. Well, it is much easier for them to communicate with the people who are in the same country with them. And it is more difficult for them to talk with foreigners. But making friends with foreigners is beneficial for their overall development. And always staying with people who speak the same language with them is not good for the overall development. Well, table 1 just gave the summary of the results we just mentioned. Well, then we want to compare the other two cases, the benefits with decay and with the first cost function and with the second cost function. And proposition 5 says, no matter which the utility function is defined, if these conditions are satisfied, any inner star network regarding partition delta is stable. And in this proposition says, regardless of the utility function, if these conditions are satisfied, then inner complete network regarding delta is stable. Well, here we can see that it seems that there is no difference between the two cost functions for the two results because the sufficient conditions are the same for the two cases. Well, here, what is the reason? Because there is a common feature between the two kinds of networks. That is, there is no connection or there's no link between players in the different groups. So the second cost function cannot work for this kind of network structure. And proposition 7 and 8 give the different sufficient conditions for a complete network to be stable for the two cases. Well, this condition is more strict. And to feel the difference between the two results, let's see numerical example. Here, the parameters or the decay factor delta is given such that the condition here is not satisfied, but the condition here is satisfied. And after our check, we find that this complete network composed by 6 players is not stable in K3, but stable in K1. But now, if we change the delta factor, or we see the damage of the benefit to a very small number, then the network G is stable for both cases. Why? Why is it? Because when the damage for the benefit, or we say the decay factor, is small enough, then players prefer to form as many as possible the links to try to decrease the damage of the benefits for connected players. And table 2 just give the summary of the results we just mentioned. Well, for model 1, we finally consider a very special class of partitions where there is only one group containing more than one player. And for any other group, there is only one player. So for this special class of partitions, we obtain that regardless of the utility functions 2 and 4, any non-empty stable network is minimal. And the two results give the different sufficient conditions for any stable network to be minimally connected. Well, it's easily see that this condition is more strict, and F1 should be small enough. And to compare these two results, let's see example 5. Here the parameters are given such that the condition here is not satisfied. So it's possible for us to find a stable network, but not minimally connected. So let's see network G in figure 6. There are 4 groups, only the third group containing more than one player. And we check that this network is stable under case 4. And why? Why is it? Because for player 2, if he forms a link with player 1, then it will increase the average cost for the 3 links. So this not connected network is stable under these conditions. And here I'd like to ignore the description of the results here, but I'd like to see that the difference of the two cost function is not so obvious for the special class of partition. Why? Because the two, how to say, the two cost functions are different only for between players from the large group and the players from the single group. And it is the same between players all from the single group. So the two cost functions are not obviously different for this special class of partitions. Well, now let's move on to model 2. Well, here in this model, we continue to consider stable network, but just in a dynamic way. The network formed after a process of players' interaction. And we adopt the first two utility functions, with the first normal cost function and the benefits with decay and benefits without decay. And now let's describe the dynamic process. The game is of infinite horizon, and the time is discrete. And the players start with an empty network at stage 0. And at each following stage, a pair of players is randomly chosen to update the link. For instance, at stage K, if pair IG is selected, player I chooses an action AIG. If AIG is 1, it means that player I agrees to form the link or not to sever the link if it already exists, and aij equals to 0 for the other two cases. And we need to mention that the link is formed or remained only if both the players agree to do so. Well, most importantly, the game is of incomplete information, which means that when the pair is selected, they do not know the label of each other. As a result, they don't know the exact cost of forming this link. But each player has his belief hi. It is a m-dimensional vector, with hik is the probability that player I thinks he can meet players in group K. So we can define EI here as the expected cost for player I to form a link with a player he doesn't know. And for the incomplete information, there is information updating rule, under which if players were ever connected, they will know the exact label of each other. Otherwise, the belief remains here, the prior one. Now let's formally define the strategy of each player in the game. Here, I tau, J tau is the pair selected at stage tau, and gamma t, a sequence of pairs, is the selection path to stage t, and G tau is the network formed at stage tau, and sigma t is the combination of pairs and networks, is the formation history to stage t. And sum t is the set of all possible formation histories to stage t. Well, actually, in this game, a pure strategy should provide the player the action, no matter whom he meets and no matter what the formation history before he is selected. So, SI, a pure strategy of player I, maps from the formation history and from any player he meets to the action. Well, below we have a very interesting assumption that each player is myopic. Each player chooses the action to maximize his current expected payoff when he is selected according to what he has obtained the knowledge. And here, BI is the updating function of player I, which maps from any formation history to the set of players that player I knows the exact group labels. And WG maps from the any formation history to the component containing the direct links of player G. Actually, it is the subnetwork constructor containing all the direct links of player G. And YI is the combination of the two parts for any sigma t and for any player G. So we again define the strategy of player I. SI is a pure strategy of player I, which maps from no matter whom he meets, no matter what is the situation or what is the structure about the player, and no matter what he has learned before, to an action. So with this assumption, we consider a very special strategy profile. S star is called a stable equilibrium if for any player I, he decides to form the link or not to sever the link, if and only if this inequality holds. Here, the left hand is the expected payoff of player I when he decides to form the link or not sever the link. And the right hand is the exact payoff of player I if he decides not to form the link or sever the link. Well, since no matter the left hand and the right hand is well defined, so we are sure that the stable equilibrium exists and it is unique. Under the stable equilibrium, we now define the stable network in this game. So when players play the stable equilibrium, a network G is called a stable network under complete information if there is a selection path, after which this network appears. And for any subsequent path, this network will never be changed. And the definition of stable network under incomplete information can be also defined in a similar way. Well, for this definition, there is a very important point that when we see a network is stable, there must be a associated selection path. Well, in other words, that it is possible that after different paths, the same network appears, but we can see that this network is stable for one selection path, but it may be not stable for the other selection path. Well, to show this, let's see the example 6. There are 7 players and 3 groups, and the parameters are given here, and the prior beliefs of each player is given in table 3. For instance, let's see player 3. Here 1/8 is the probability that player 3 thinks he can meet players in group 1. And 3/4 is the probability that he thinks he can meet his partners in the group 2. And 1/8 is the probability that player 3 thinks he can meet players in the third group. So let's now consider 2 different paths. One is of 10 stages, one is of 2 stages. Well, figure 7 shows the network formation process under this selection path, under incomplete information. So we can see that after stage 10, this network emerges, and we checked that it is stable. Well, under this path, after stage 2, the same network emerges. But we checked this network is not stable for this path, because if at stage 3, the pair 2/4 is selected, then this link will be formed, so it is not stable. And another interesting point for this example is that although this network emerges and stable after stage 10, but the information is still not complete, which means that there are still some players do not know the label of each other. Well, now let's consider another path, a path of 12 stages. Well, figure 9 shows the formation process under this path, under incomplete information. We can see that at stage 12, this network emerges, and we checked that it is also stable. But for here, the information becomes complete. Why? Because at stage 6, at stage here, at this stage, all players are connected. So at this moment, from this moment, all players knows the label of each other. So the information is complete. Well, now let's see several observations. Here, proposition 9 says that if the utility function is defined that there is no decay for benefit for any 2 networks which appear in the process of complete information, then the network formed before is a subset of the network formed later. Well, the equivalent saying of this proposition 9 is that under complete information and without decay, once a link is formed, then it will not be severed again. Well, this result does not hold for other 3 cases. The cases of complete information with decay, incomplete information with decay, and incomplete information without decay. So after we get this result, we are wondering that whether this result will influence the difference on duration to stability. So we then do some experiments, and we get this figure. Well, in this figure, the x-axis is the number of players, and the y-axis is the number of stages to the appearance of stable network. Well, there are 2 obvious observations in this figure. One is that as the number of players is getting larger, the duration is getting larger for all the 4 cases. Well, it is easy to understand because as the players get larger, the interactions between players becomes more complicated. And another observation for this figure is that the case no decay and complete information, the duration is much slower. Well, we find that actually this result is the main cause for this, because for the other 3 cases, there is the process that a link is formed and then it's severed. There is repeat process, but for this case, there is no such repeat process. This is the main reason for the low duration to stability. Well, to better feel the difference on the duration, let's see the simulation process for a 15-player game. Here, there are 3 groups, and all the other parameters are given. So now the first video we'd like to see is the case and incomplete information without decay. And I'd like to remark that at the end of the video, the network formed is stable. It is about 314 stages to stability. And the second case is incomplete information with decay. We can see that the process is more complicated because it is with decay, so there is a circle emerges in the process. It is much longer because it's 387 stages. And this, we can feel that it is really a short time because it is under complete information and without decay. It is only 29 stages. Start and finished. And the last case is complete information with decay. It takes 236 stages. Okay. And then we continue, and we'd like to introduce a definition of heterogeneous link. Well, given a partition delta, a link IG in network G is called heterogeneous if the 2 players IG are not in the same group. And proposition 10 says that if the utility function is defined that no decay, and if F1 is bigger than 1, then for any stable network formed and complete information, and for any heterogeneous link IG, player I must have the neighbors in the same group with him. But this result not always true for the case of incomplete information. Well, finally, let's consider a very special partition and the beliefs of players. There are only 2 groups with the equal number of players, M. And since each player knows the exact number of players in each group, so we give the belief here. Here, 2 times M minus 1 is the total number of players that player I don't know the label. And M minus 1 is the number of players that player I know who are in the same group with him. So under this special partition and special beliefs, when these conditions are satisfied, then for any network, for any stable network under complete information, this network must be connected. Well, for any stable network formed under incomplete information, the network must be empty. Well, what's the reason for such? What is the reason for the result under such parameter? Because under these parameters, for each player I, the expected cost EI is bigger than 1. So no one prefers to form any link under incomplete information. Well, so in Model 1, we mainly examine the stable network, the conditions for some special network structures to be stable. And the major contribution is the comparison and the four utility functions. And in Model 2, we construct a dynamic network formation game with infinite horizon and with incomplete information. And we mainly compare the results formed under incomplete information and complete information. Well, to be honest, for the second model, we are still in the process. And there are two issues we are now dealing with. One is the overlapping group partition, which means that a player can belong to several groups at the same time. And in this case, we can define the utility of each player involving the matching degree of two players. Well, the matching degree of two players is the proportion of the groups they commonly belong to. And the second issue is that we propose another information updating rule, which is called superior updating rule. Under this updating rule, players can not only update their information for those players they are connected, but also update their information for those players they are never connected. Because if players know the exact number of players in each group, and after some process, he knows some players, then the proportion of the players he don't know in each group is changed. So the comparison of the two updating rules is very interesting. And these are the main references for our work. And that's all. Thank you so much for your attention.